Okay, any questions before we start? Okay, so if you remember, the last thing that we were discussing was the transformers. And the idea of the transformer is we have a usually iron core, and you have coils on both sides. And if you send an AC current through one side, which is called the primary, and let's say you have NP turns of wire on the left, and then on the right you have another coil, and here you get, let's say, Vs, the secondary coil. And let's say it has Ns turns. This is called the primary coil. This is the primary coil, this is the secondary coil. Now, the idea is that you send some current, an alternating current, on the left-hand side. The alternating current creates a magnetic field, which is itself changing in time. So, in this solenoid, you create a magnetic field. And the iron, which is called a ferromagnetic material, the property of iron is that it first enhances the magnetic field, and secondly, it traps the magnetic field lines. So magnetic field lines, you see, if you have a single solenoid, and if you would send some potential, an alternating potential through that solenoid, the magnetic field lines will just look like this. They will spread out. Now, but what this core does, it traps these magnetic field lines, so they don't spread out. They start from the primary coil, they are trapped in the iron core, and those magnetic field lines pass through the secondary coil. So, whatever magnetic field line passes is created by the primary coil, it passes through the secondary coil. And the flux is the flux passing through the primary coil over the flux passing through the secondary coil just becomes the ratio of the number of turns you have. So if you look at how much potential is created in the secondary coil, well, this is by Faraday's law. This should be equal to minus d phi p d phi s by dt, the rate of change of the flux passing through the secondary coil. Well, but this is nothing but ns phi p over np. Phi p is the flux passing through the primary coil. The number of turns, they are just constant, so this is a ns over np minus the derivative of phi p by del t. This is the flux passing through the primary coil, the rate of change of flux passing through the primary coil. But again, by Faraday's law, that is nothing but VP. So Vs over Vp is just ns over np. So this gives us a way to increase the potential or decrease the potential of an AC potential difference. So for example, if you see there are wires that cross countries, they are usually called high tension wires. You have probably seen them, right? Why do we go to high potential to transfer the alternating current? Why not just, I mean, let's say if it is created as 220 volts at the source, why not just transfer it as 220 volts?
Over large distances, the resistance of the cables is maybe too significant.
Well, let's see. We had already seen that the power dissipated by a resistor is I times V. The current running through it multiplied by the V. And what else do we know? V is I times R. So this is I squared times R. Or, if you like, this is equal to I is V over R times V. This is V squared over R. Right? So why do we increase V? Now you see, this is the power dissipated by the resistor. No?
Because of the conservation of energy, the power will have to be initial and end power must be equal. So to be able to do that, we have high potential that wires.
Well, let's see. The current through the primary coil multiplied by the potential passing through the primary coil will be equal to the current through the secondary coil multiplied by the potential at the secondary coil. So this will be always satisfied. So if we set Vs, if we increase Vs, the potential at the secondary, then Is will drop. The current will become, if we increase the potential by, let's say, 100 times, the current passing through the secondary will be reduced by a factor of 100. So you are essentially reducing the current, and hence the power dissipated by the resistor will be significantly reduced. Now, any questions on Ampere's law, no, Faraday's law, induction, transformers, etc.?
Hocam bir akım voltajı arttıkça akım nasıl azalıyor?
So the question is, when is this valid? Well, alternative in the case of alternating current, well, you say this is the here. This is valid for an alternating current.
Ama R yerine Z yazıyoruz normalde.
Yes. Well, you see that is for maximum values. Not for instantaneous values. Any questions? Now, let's see, what does the transformer actually do? Let's study it in a bit more detail. So on one side, we have something that creates a magnetic field. And then there's something else nearby that is influenced by that magnetic field. So the current that you send to one side of your system, it creates a flux in the other part of the system. So let's forget about the core. Let's just imagine you have whatever you like, some number of turns. And you have some power source, you send some current through it. And in the near vicinity, even it might be around it, you have another loop. Let's put a resistor over there. So here you create a flux and a magnetic field. The magnetic field lines, in this case, there is no core, so it will just spread out. Some of them will also go through this other coil. So there you have another current, phi 2. Well, this phi 2, you see the flux is magnetic field times the area. Phi 2 will be proportional to the magnetic field created by the first current. But B1 will itself be proportional to I1. If you remember, we have the Biot-Savart law. This is mu0 over 4 pi I dl cross r hat divided by r squared. This was the magnetic field created by a current carrying wire. So the magnetic field, no matter what the shape of the wire is, the magnetic field will always be proportional to the current. So the magnetic field in this coil will always be proportional to the current passing through this first circuit. And the flux is magnetic field times the area. So the flux in this circuit will always be proportional to this B1, which is itself proportional to I1. So this phi 2 will always be proportional to I1. So as long as you don't change the shape of your system, phi 2 will always be proportional to I1. Just like in the case of the capacitor. You see what we had in the case of the capacitor. If you put some charges in the capacitor, you create a potential difference. And that potential difference is always proportional to the charge of in the capacitor, unless you change the shape of your capacitor. And that proportionality constant depends on the shape. Well, more or less a similar thing will happen over here. The flux passing through the second circuit will always be proportional to the current passing through the first one, and that proportionality constant is called inductance. This is M21 is called mutual inductance. Of course, this constant will depend on the geometry, will depend on whichever material you put in your system.
What if there was a current running in the second?
Well, if there is a current running in the second system, you see, let's suppose you send the current through this conductor. This will create a magnetic field. And this magnetic field will be non-zero here. So there will be a magnetic flux created in the first coil. And so the magnetic flux created in the first coil will be proportional to the current that you send from here. So it will be phi 1 will be M12 times I2.
Doesn't it affect the flux in itself?
Well, you see, let's first make some definitions. Then we can look at how to use them. Let me, if you like, let me put phi 2,1 and phi 1,2. Phi 2,1 is the flux created in the secondary coil due to the current in the first coil. Phi 1,2 will be the flux created in the first coil due to a current in the second coil. And as your friend pointed out, we can even define phi11 as M11 times I1. This is the flux created in the first coil due to the current in the first coil. It will be proportional to the current in the first coil. And if you like, we can also define phi22. This is the flux created in the second coil due to the current in the second coil. Now, these M12 and M21, they will always be equal. Since it's just basically a geometrical factor, they will always be equal to each other. This M11, which will usually be denoted by L1, M22, let's call it L2, these are called the self-inductance. These are basically the definitions that we will be using. Now let's calculate an example of this mutual inductance. Well, we already know the solenoid. Let's assume we have an infinitely long solenoid. And let's assume we send the current through the solenoid. What will be the direction of the magnetic field created by this current? In that direction. Just wrap your fingers towards your left. No. Yes. Well, let's just imagine inside we have another ring with a radius r. Let's also look at the case where we have a ring outside of radius r prime. What is the mutual inductance of the small ring? What is the mutual inductance of the large ring? Well, this inductance, whether mutual inductance or self-inductance, will be the analog of capacitance. If you remember when we were trying to calculate the capacitance of a certain system, what we did was we put some charge, and then we tried to calculate the potential difference created by that charge. Well, similarly here, we send a current, and now we try to calculate what is the flux passing through this red ring and what is the flux passing through this blue ring. Now, what is the magnetic field created by the current I? Do you remember? Well, let's make a review. What we do is what do you remember about the magnetic field inside the solenoid? They will be straight lines, magnetic field lines. Let's try to use the Ampere's law. So to use the Ampere's law, what we did was we took a loop. This can be our loop of length, let's say, L. And Ampere's law told us that B dot dl around this loop should be equal to mu 0 times I enclosed. Well, we already know that B is in this direction, and only inside the solenoid, there is no B outside, so there won't be any contribution from this side because B and DL along this side will be perpendicular to each other. B and DL along this side, they will be perpendicular to each other. B is 0 along this line, so there is no contribution from that segment. The only contribution is from this segment, where the magnitude of the magnetic field will be constant along that segment. So that integral, B dot dl integral, just becomes the magnitude of the magnetic field times L. And the right-hand side is mu 0. Well, let's say there are n turns in that region, in that length L, each carrying a current I. So the total current passing through my loop will be just n times I. So if we divide by L, B just becomes mu 0, small n times I. Small n is the number of turns per unit length. Okay, so now we know the magnetic field. The magnetic field is uniform. It doesn't change from point to point, so which simplifies our computation of the flux. So what is the flux passing through the red loop? You see, the definition of the flux was B dot dA. This is how we define the flux. B is constant, so just take it out of the integral. And what is the direction of dA? You choose. Let's choose it to be in this direction. So B is in this direction. dA is in the same direction. So B dot dA is just the product of the magnitudes. B, the product of B is constant, mu 0 and I. The integral of dA. What is the area bounded by our ring? Pi r squared. Well, as I claimed before, the flux created inside this ring is proportional to the current passing through the other wire. And that proportionality constant is what we call the inductance. The radius of the solenoid, let's say, is 2d. The radius is just d. Now, what about the inductance of the blue ring? Mutual inductance of the solenoid and that blue ring. Again, we just first send the current, which creates the magnetic field. And we had already calculated the magnetic field. Now, what is the flux created that passes through this blue ring due to that magnetic field? Mu 0 and I times pi d squared. Mu 0 and pi d squared times I. Why pi d squared and not pi r prime squared?
There's no magnetic field outside the...
In this area, between the solenoid and the ring, there is no magnetic field. So there is no contribution to the flux from this area. The only contribution to the flux is from this area. So let's call it M2. This is equal to mu 0 and pi d squared. Now, an alternative that we could have done, at least in principle, maybe not in practice, but we could have just send a current through this red loop. Then it will create a magnetic field. And that magnetic field will create a flux inside this wire that goes around the solenoid. And we could try to calculate that flux. And that flux, from that flux, we could just extract the mutual inductance, and we will end up having exactly the same expression. So it doesn't matter. I mean, if you have these two systems, it doesn't really matter through which one you send the current and calculate the flux of the other one. Whichever one easier, just do that one. Any questions? Okay, let's do some examples. There's not much topics left already, and we still have some time, so let's just do some examples. We will continue with this inductance on Thursday. Let's get this problem. So we have two rails, frictionless. On them, there is another rod, and the whole system is in a uniform magnetic field. So the first question, let's say that we have this system, and then the rod starts, we just push it, and the rod has some initial velocity, let's call it V0. So how will it move? What will it do? These rails, they are frictionless, they are not connected with each other. Suppose we push them and we give it some initial speed V0, and then what will it do? How will the current go? They are not close. In the first part, it's not close. So let's start from the zero. Let's assume we start pushing it. It's initially at rest. So now we started pushing it. What will happen? The wires are not close. They are not connected to each other, the rails. What happens to the potential difference? Well, the positive nuclei is a metal, they are not moving anywhere. Do they go up or down? Negative, you see, the force V cross P is V cross B, is downward, the charge is negative, so the negative charges will go up. So as we start pushing it, initially the electrons will start moving up, and hence the current, there will be an initial current that is going down. So what will be the force acting on this current? The direction of the force. In that direction. Well, that's consistent with Lenz's rule, which states that if there is an induced current, it will be such that it will try to prevent whatever is creating it. So if this current is created because we started pushing it in that direction, so it will resist. So it will try to stop. So the force will be towards the left. Well, how long will there be a current? What will the negative charge, as your friend had said, the negative charges are moving up, but there's nowhere for them to go. What will happen then? They will accumulate. So this end will be negatively charged. Well, in the bottom end, it's not that the positive charges went to the bottom end, but the negative charges on the bottom end, they moved up. So the number of negative charges on the bottom is now reduced, which means that the bottom end will be positively charged. Let's say this whole distance is d. So we get an electric field created. And the motion, the current will run as long as there is a force acting on the charges. This is the force acting on a charge. So the charges will move until the electric field has a magnitude V times B. You see, the negative charges, this positive charges over here will pull the negative charges. The negative charges will feel an electric force which is downward and a magnetic force which is upward. The magnetic force is constant because it depends on the charge and the speed. If the speed is constant, V is constant, B is constant, but E keeps on changing as the charges are accumulated at the top and at the bottom. And they will keep accumulating until the electric field magnitude is equal to V times B. Now let's ask a different question. The same system. We give it a push. Initially it is moving with a speed v0. But this time we connect this with a, let's say, a resistor. What will be its speed as a function of time? Now what will happen? Now we will have a current in the counterclockwise sense. No, in the clockwise sense.
I was thinking of where the electrons
The current will be in the clockwise. Well, it's very similar to the first one, but in the first one what we had was we had this accumulating of charges. Here the charges will not accumulate because they are connected by a wire, by a resistor. So the charges will flow around closing the circuit. Now there will be a force acting on the rod. Again, just like in the previous case, it will try to stop it. So what will be the motion of the rod? What do you expect the motion to be? Will it be a motion with constant acceleration? Why not? Or motion with constant velocity?
It can't be constant velocity because
There is a force, so it is accelerating. Okay, will the acceleration be constant? Yes or no? F is, what is F? F is equal to I times L times P. No, D times P. Well, let me just change this to L. F is I times L times B. Is this F constant? What is changing with time? The current will be changing in time. L is constant, B is constant, but I will not be a constant. I will be changing in time. Why does I change? Because V is changing. You see, V will be changing because there is a force. Since V is changing, I will be changing as a function of time. Since I is changing, the force will be changing. So it's not even a motion with constant acceleration. How can we write I? What is I? What is the current? What is the EMF? Okay, minus d phi b by dt, which is minus d by dt of b times L times x, or epsilon, ignoring the signs because we had already determined what the direction of everything should be. This will be v times b times L times v. But this EMF should be equal to I times R. So the current is B times L over R times V. Now we know the force as a function of the speed of the rod. This is I times L times B, or BL squared over R times V. Now we have the Newton's second law. Newton's second law says that m times acceleration, which is dv by dt, should be equal to the force, which should be minus BL squared over R times V. Why the minus sign? So dv by dt, the velocity as a function of time is such a function that its derivative with respect to time is proportional to itself. Do you know this function? Now, if you take the logarithm of t, let's say the derivative of the logarithm of t is not 1 over t, is not proportional to logarithm. Well, let's see, let's try to solve it using integrals then. dv by v, this should be equal to minus bl squared divided by mr times dt. So the changes in time should be related to changes in speed through this relationship. Now we can just sum both sides. At t is equal to 0, the speed is v0. At a later time t, v is v of t. Well, the left-hand side is logarithm of v, from v is equal to v0 to v is equal to v of t. The right-hand side is minus bl squared over m times r times t, minus 0. So v of t over v0 is minus bl squared over mr times t, the logarithm of v of t. or V of t is equal to V0 e to the power minus BL squared over MR times t. So it will slow exponentially. Well, it kind of makes sense. Let's say initially it is, let's say, moving fast. So it creates a large current, and this large current creates a large force. But then due to this force, it slows down. But since it slows down, the current becomes smaller, so the force becomes smaller, so its acceleration drops. It keeps on slowing with a smaller acceleration. The longer it slows down, the smaller its acceleration becomes. So it never becomes zero, but it exponentially slows down.
Sabah şey yapıyoruz ya, arkadaşa bakıyoruz maalesef. Arkadaşının devletini Mayıs'a bakıyoruz, Mayıs'a bakıyoruz ya, o da bir yer eksi yapıyoruz.
Where?
Yukarı tarafında. Bir yer eksi diyor var ya, sağda. Etrafı şey, etrafı.
Here.
Orada mesela şey alıyor musunuz? Akımın ters yönde oluşturduğu bir şey de var ya, manyetik alan. Onu alıyor muyuz?
Well, you see, a current creates a magnetic force. So you are saying that there is also the current here. This current creates an additional magnetic field in addition to this external magnetic field. No, we are ignoring that. So basically, even if there is no such magnetic field, the magnetic field created by this current will also have the same effect. But we are ignoring that. In a sense, we are assuming that that resistor is very far away, not very close to our rod. Other questions? So in this problem, we have this current carrying wire, which carries a current I, and near it there is a rod. And this rod is at a distance B, has a length A, and it is moving with a speed, let's say, V. What is the EMF between the endpoints? Now, we don't have time to solve it in all detail, but let me just give you the key points. First of all, you see, what is B created by a uniform wire, a current carrying uniform wire? Mu 0 I over 2 pi I, 2 pi R. You see, in the previous problem, here we had the EMF was B times L times V. We could use this relation because B was uniform. Throughout my rod, B was uniform. But in this problem, B is not uniform. So B at this point is different than B at that point. Now the trick is, as usual, if there is something changing, and if you know the answer for something that is constant, well, you have your extended system divided into very small parts. Now, each one of these very small parts, within each one of them, B is constant. let's say they have a length dr. So the epsilon, due to that very small segment, will be b at that point. Its length is dr, and its speed is v. So the total EMF would be just the integral of mu 0 I over 2 pi r times v times dr over r from the point B to the point B plus a. Or no, mu 0 I over 2 pi v logarithm of b plus a over a. Okay, on Thursday, we will probably finish most of the topics that will be covered in the final. So next week, I will spend more time on solving examples throughout about all the topics we have discussed. So if you have any questions, let's prepare it for next week. B. Correct. So see you on Thursday.